Malachi probably has the largest slide deck we've seen in this conference ever, but we'll see. So he's from MITRE, but this is independent work. And his fun fact is that he did a PhD at Georgia Tech and thought he'd never have to do maths again when he came into cybersecurity. Wrong. Totally wrong. So he's going to talk about memory forensics. Thank you.
Okay, thanks. All right, so cool. Let me get my timer so I'll make sure I don't go over. All right, so this talk came about, I was interested in memory forensics, and I had a strong background in game theory because that's what I did my PhD in. I was like, well, I suffered through all this PhD process, so how do I, how can I justify, going through this process? And there's like machine learning that popped up, and I realized that there's a lot of math and machine learning that I can leverage and I can learn and use for cybersecurity applications. And so I started this, 2 years ago as an independent work while I was working at Booz, outside of Booz Allen, and I've continued on now being employed with MITRE. So that's that. So just about me real quick. As she mentioned before, I had my PhD at Georgia Tech. I did my PhD thesis in cybersecurity and game theory. I've done a lot of vulnerability security and also embedded security at Booz Allen, now currently MITRE. So that's the highlights. All right, so here's the layout for this talk. So I'll motivate the talk, and really that's more about framing the problem. So what problem am I going after, and why is that a well-motivated problem to pursue? We'll talk about memory acquisition automation briefly because the time limit, I'll have one slide on that. But the meat of this presentation is on the phase 1 detection and phase 2. So phase 1 is more about static analysis. Phase 2 is more of the dynamic analysis. And then we'll conclude with a conclusion, and we'll, of course, have Q&A. And so another thing that makes this slide deck longer is that there's a lot of details in these slides that, because of the time for this presentation, I can't put in there, but I added to the appendix so that way you can refer to them offline or if we have Q&A. So that's another way to kind of get more out of this. So with that said, we'll press on. So motivation. So code injection is a technique that is used by malware to basically place malicious code in a legitimate process in our library to force a legitimate process to execute that code on the malware's behalf. So there are two examples here. One's the PE injection, other is DL hijacking. So for the PE injection, you can think as the target process, pre-injection, there's the image where the binary that's running in memory is at, and there's some free space. And so what the malware will often do is it'll overwrite that free space with its code block and spawn off a thread that executes processes or threads that look like it comes from this target process. DL hijacking is another approach where you basically do a substitution attack where instead of the actual DL being loaded, malicious DL is loaded. And so in addition to those, do you have other techniques like PE injection or like process hollowing and reflective DL injection? So those are just some examples of what we have to go through. And so some of the techniques to kind of address this are emulation and hooking. And so there are modern techniques that are employed by many of the antivirus vendors to monitor the execution behavior of the binary on the target host. These techniques combined with execution behavior analysis can allow for a discovery of advanced persistent threats that leverage advanced code injection techniques to hide in memory and disguise execution. So one of the problems is, and this is really the problem statement here, is that hooking and traditional emulation techniques can be reliably invaded by malware. So as an example on the hooking, malware, they can either use lower level unhooked API or remove the hooks at runtime. So that's one way that the malware can get around the hooking. In terms of emulation, a lot of the malware has built-in techniques to detect if it's in an emulated environment, so if it's running in a virtual machine. So as an example, what the malware could do is, a lot of times on emulation, you're emulating the API, and so the malware can look for quirks in how some of the API may not be implemented properly and detect that. And so typically, if it knows it's in this emulation environment, it can modify its behavior, so that's not useful to you as an analyst or a defensive person. So those are just two examples. So one of the observations that I'm pointing out right now is that a necessary condition for malware malicious code to be executed is that it has to reside in memory prior to and during execution, so that's the truth. So as a consequence, you can imagine that live collection of memory artifacts can provide an effective means for identifying these malware residing on a host. And so here's the objective of this talk. So what we want to do first is demonstrate an approach that allows us to compare memory artifacts across a set of network hosts. in a scalable manner to identify anomalous code. And so the types of artifacts we're interested in are processes, shared libraries, kernel modules, and drivers. And then specifically, we want to discuss how we can use an approximate clustering algorithm to leverage to be leveraged so we can identify outliers in that set of equivalent artifacts. And we also want to be able to discuss how we can use some dynamic binary analysis techniques to improve our detection of sophisticated malware threats. So that's the objective. All right, so at the high level, here's the main takeaways from this presentation here. So what we have here is this is the automated malware detection process here. So as you can see here, you have your set of hosts, and this is just an example of a binary that be in memory, your explorer.exe. So there's a static analysis process. We do some clustering, which leads to some anomaly detection. So at that point, if we've identified an anomaly, then we pass it on to the dynamic analysis, right? And that way, it allows us to get a better understanding if this is really benign code or is it really malicious. And so those are two phases of that. So this is like the steps of the process. So you can imagine you have a set of network hosts on a corporate enterprise environment set up, and you can have an agent installed on each of the hosts that basically periodically collect and send memory artifact data to the server. And so you have this collection server here that collects this data and organizes it. And really the key step here is that once these are collected, the identical types of artifacts are clustered. So you can imagine here, this is an example where you have these few hosts, they're very similar to each other. You have these hosts here that are similar, and you have this outlier. So that's really interesting when you have the outlier. So the next step would be, if you had this outlier, to pass it on to do some dynamic analysis to try to figure out, is it really malicious or is it benign? All right, so I'm briefly going to talk about memory acquisition automation, but we don't have a lot of time to cover this, so I'll keep this pretty short. But the main idea here is that Recall is an open source tool that you can be used to collect live memory from your computer and perform analysis. And so one of the things that I developed was a Python agent that can be deployed on each host on a Windows 7 system or Windows 10 system to collect these memory artifacts and send them to this collection server. All right, so this is really the bulk of the presentation where we talk about the phase 1 detection, which is the static analysis. So as we see here, the overall goal here is to group the memory artifacts based on their similarity to identify those outliers. And we want to leverage dynamic analysis on the ones that we do see as outliers so we can figure out if it's really an outlier or not. And so what are the requirements for clustering? So if you want to do this at scale, computational efficiency matters, right? So you need to be able to do this pairwise very fast. And also you want a clustering algorithm that has a favorable runtime. So linear is really ideal if you can get it in the worst case. So that's really the two requirements. And we're going to spend the rest of this time in this phase 1 talking about that. So pairwise, so I use the n-gram approach. If you're really curious about how I did that, there's Appendix C we can discuss in Q&A, but basically you can think of, we have a way of representing a binary, that execution behavior as a vector. So you have these binaries and you can map them into this vector. And so if you can do that, the next step is you can think about a similarity function. And so a similarity function where we pass in these two vectors and output is values from 0 to 1, where 1 means that they're a perfect match and 0, they're dissimilar. And so from that, we can measure the similarity of those two binaries. So the question is, what should a similar function look like that we want to use? And so that's what we'll talk about next. So one of the approaches that I considered was a Jacquard index. This is an approach that's really simple. There are a lot of different types of similarity measure functions that you can use, but I thought this was pretty simple. And so this one's really simple in the sense that you take the common number of n-grams over the total number of n-grams, and so that gives you your value. So 1 means that they basically match, and so that's a way you can measure the similarity of the two binaries, at least their execution behavior. And so one of the questions is how does this perform in practice? So we have this theory here, but how do we evaluate this in practice? And so one of the ways I did this was I looked at the in-memory copy of an executable, so explorer.exe, and I compared it to the on-disk copy. And the reason why I did that is that I'd expect intuitively that they should be similar, right? The one in memory should be similar to the one on disk, but there are likely to be differences, and the reason is that on an operating system, the save space, it pages some parts that aren't executed in memory to disk, and so that's where you're going to get those differences. So some blocks that exist on disk aren't in memory, and so that's where you could get those differences at. And so I've developed a tool in Python to run that, to do that similarity analysis, and it gave me this value of 83.4% similar. So that looked pretty reasonable. So I was like, okay, that sounds good. But now the next question is, is there a way for me to benchmark this similarity? And so, of course, the answer is yes. So I looked at bindiff, right? So I did that. I ran these two exact binaries on bindiff, and I got this value here, 84% similar. So I was like, okay, that's pretty good. So right now you guys are thinking, so why did I do all this work if I could just use bindiff? And so the key thing here is scale, because the performance really matters. So with bindiff analysis, it took 4.2 seconds. With the Jakarta performance that I used with my algorithm, it was 57 milliseconds. So that's a speed up of 74, which is pretty substantial. And if you think that all this was run in pure Python, so if I did this in C, you get even more speed up. So that's one of the key points there is performance. So although these examples we're talking about comparing the similarity of two whole binaries, you could also use this on a function level, so you can compare how similar two functions are. So you can use this technique for that also, very similarly. All right, so I know I'm going pretty quickly, but there's a lot of content I wanted to cover. So the next step we're going to talk about is now we've defined pairwise similarity analysis. Now we're going to talk about groupwise similarity analysis, and that leverages what we talked about before. And so there's a particular approximate agglomerative clustering approach that we're going to talk about, and it's based on a paper that I'll show you in the references by Professor Konrad Rieck. He published a paper that was really awesome in 2011, and basically that approximate algorithm has a runtime of ON, so it's pretty favorable. The primary reason why I preferred using this clustering versus k-means is that k-means you have to supply the number of clusters a priori, and so with this particular setup, it would be kind of difficult to do that, and so that's why I favored the agglomerative clustering approach. So here's a sketch of how the approximate clustering algorithm works. So you can imagine you have a set of binaries here, say 1 to 99,000. And so step one is you do a prototype extraction. So with the prototype extraction, there are prototypes for small representative sets of those binaries. So you can think of these binaries here are representative of the overall set here. And so the key thing here is that instead of performing the clustering on the whole set of binaries, you perform the clustering on just those prototypes. So that's why you get this performance of k squared log k. And since k is very small compared to n, that's why we get the linear term here. So that's really the idea here, is that we're able to cluster these prototypes. And so the next step after that is the binaries inherit the clustering assignment of the nearest prototype to them. So these prototypes, well, any binary that's near to this guy right here will inherit his cluster. And so that's really the idea with this approach. And so it's pretty favorable. And so if you added a new particular binary to the set, you can think, here's an example here, and if it's similar enough, it can be assigned to a prototype, or if it's too dissimilar, it can be its own prototype. So it can either be associated with one of these binaries here, or it can be its own. So that's really the idea there. All right, phase two. Detection, this is where we talk about the dynamic analysis, and just kind of recap. So phase one is like we identified a static analysis, through static analysis, the anomaly, but we don't know for sure if that's really malicious or is it benign. And so this is where we try to identify that better. And so one of the key things at dynamic analysis is it can be more accurate, but the problem is it's computationally more expensive to do. And so that's why we had this phase one phase as a pre-filter, so we don't have to spend a lot of computational effort on all those binaries because it doesn't scale in terms of enterprise environment. So what we'll focus on here is more on a dynamic analysis aspect here, and so this is where things get pretty interesting. And typically with binaries, they utilize system calls and API to interact with the operating system to perform meaningful operations. And so a corollary to this is that by analyzing those external call sequences of a binary, you can understand the underlying behavior of what's going on. So the next slides, I'll walk you through like a quick example of some malware that's in classic malware that's in IDA. So this is a real malware here that I was loading in IDA. It was based on Windows XP system. And so on the left side is a control flow graph, and on the right side is this assembly of that particular code. And so just by looking at this assembly, and particularly the calls that are being made here, it gives you an idea of what's happening with this binary. So it turns out with this particular binary, or this malware, is that it iterates through the process handles. So it calls this method and this process 32 next, where it iterates through these process handles. and it's looking to see if there's a process that exists that's called explorer.exe. And the reason why we care about that is that that's to check if the user is logged in. So if explorer.exe exists, then we know the user's logged in. And so at that point in time, if that process exists, it'll spawn a thread to infect the target system. And so just by really looking at the call trace, it tells you a volume of information about what's going on in terms of the binary or that malware. And so here's the steps that I took to kind of do that. So you can imagine you have this binary or memory artifact, you disassemble it in IDA or Binary Ninja. You lift it to VexIR, which is an intermediate representation language, and you perform some emulation on that, and you can generate the call traces. And so those are the 4 steps that allow us to kind of do that. And so this is 5 minutes. So this is the disassembly. This is just a more detailed example here. So this is x86 instructions here. And the next step is we convert it to this intermediate representation language right here, and then that's where we can emulate that information, that code to figure out where the calls happen at, so we can get this call trace. So at a high level, this is the phase 2 process. So you can imagine you have explorer.exe, you perform all the call traces, you can map that to a particular vector, you can do the call tracing on other trusted binaries into this unified call trace vector, and what you can do here is you can do a comparison function on your target vector, or that binary you're looking at, plus with respect to the trusted vector. So the comparison function is how much of the engrams that are trusted does your target vector have. So 100 would mean all the engrams that are in your target vector are part of this trusted vector. A 0 would mean they're none. So that way it gives you an idea, are there any engrams that are likely to be malicious that are in there? And so here's an example where I wrote a Python tool to be able to actually do this using the approach that I just described. And so this is just a screenshot of one particular call trace. So I started with this function here, this sub function here, and this call trace turned out to be a link 22. As you can see here, we can see all the calls that happen in the library that is associated with. So we can see like there's a memset that happens, there's a get windows long. So there's a lot of GUI operations here, and there's like a memset operation. So that allows us to kind of characterize the behavior of that binary, what it's actually doing. All right, so this was pretty quick, but I was moving at a pretty fast clip, but I think there's a lot of information here, and I think it's pretty cool stuff. And just to kind of just back up for a minute to kind of zoom in and kind of describe what we've talked about. We've talked about this automated malware detection process here, where we have all these set of hosts, and we're collecting memory artifacts and we're clustering them based on how similar they are, and we're doing anomaly detection. And if we detect anomalies, then we pass them into the dynamic analysis to see if they're really just anomalous benign code or is it malicious. And so we leverage these two both to really help us with our detection. So just to kind of wrap this up, so security's hard. Why not make it harder for the adversary? And so one of the key aspects here is information asymmetry, right? So we assume that the network defender has information that the attacker doesn't have, in the sense that he knows the behavior, or he can collect that memory artifacts across all of the system enterprise of machines, whereas the attacker, that's a lot more difficult for him to do. And so given that the network defender can get that information or require that information, he can leverage it to figure out what the anomaly is and what's not the anomaly. And so that's really the idea behind this, is how do we flip this problem on its head and focus more on the information asymmetry and exploit that. And also, one of the things that we really want to do here is we want to require the adversary to develop techniques to challenge these types of approaches that are both reliable, so their techniques have to have fewer bugs and be portable across the different versions of the operating system. And one of the other things that makes this method very, very difficult to defeat is that operating systems change over time, so they're not static, so you get an update like every week or so. And so even if the attacker could emulate a particular set of binaries or whatever, that's going to get updated over time, like even your applications that you use, your operating system itself. So a lot of things are changing. So that works well for the defender, and it makes it very difficult for the attacker, because he has to figure out what does normal look like, and normal keeps changing as the system gets updated. And so that works favorably for the defender and not favorably for the attacker, and that's exactly the problem that I want to take advantage of and that I want to exploit here. And so really, that's really what I had to say here. The first paper here is really the key paper that I really launched this research. I read this paper like 2 years ago, and I was like, wow, there's like, if I could compare this with memory forensics and binary analysis, I could do some pretty cool stuff. And so, and this was the outcome. This talk was the outcome of that. There's some other papers on here in terms of anti-forensics, memory resilience. And there's a lot of pretty cool stuff. There's the antivirus hacker's handbook, which is pretty interesting in terms of techniques that antivirus hackers use to defeat antivirus systems. So with that said, I'll cede the floor to the audience for questions.
Thank you so much. This on? So let's get the first one out of the way.
Okay.
Apparently, every time you give a talk, people say, why don't they just hash the memory image? So let's do the thing.
Yeah, so that's one of the... So one of the questions are, why do I not just hash the memory artifacts across the PCs, and will that work? And so the reason why that doesn't work is that the hosts typically they're going to look very different, right? So if you think about, like I said before, you think about when you take a memory capture of an image in memory, it's not guaranteed to match the memory that's on, or the image that's on disk, because the operating system over time, it's going to, blocks are things that aren't being executed. Code blocks are going to be paged to disk, and so that's where it's going to look very dissimilar. So it's possible that you could take the hash of two things, and the hash is going to be very different. But when you do a similarity analysis, like what I showed, it'll be like 99.9% similar, because most of the code blocks are the same. Only a few that are missing, and those few are enough. Of course, it's going to be enough to change that hash so it looks different. So that's really one of the questions that I always get.
So we're just kind of getting into the beginning of like baking ML into hardware, like we're seeing NVIDIA start to really get into this. In your phase 1 pipeline, we're comparing memory from a lot of hosts. Do you think you could recast this problem as a temporal comparison on a singular host? That way we could have some sort of hardware level ML that's directly interfacing with that memory without requiring us to go and synchronize across the network and do defense that way?
So you could do that. So you could do it like on just on a single host where you can just capture those, and that could be effective. The only challenge there is that your baseline, you get to that classic problem of how do I train my base? What does my baseline look like, and where do I start it at, right? And so that can be tricky because the computer can change over time. Like I said, you get an update, and so that changes the behavior. And so at what point do you change? At what point do you restart what your baseline looks like? Whereas if you do like the static snapshot over the whole whole network, you have a better idea what normal looks like even as things change. And so that could work. It's just that you have to be aware of that problem.
I'll ask a question,
okay.
And then just one comment. So one of the reasons you also can't hash memory is relocations and ASLR. So as you move, you said XP, but as you move to Windows 7, especially Windows 10, the operating system is actually going to take, when the compiler says this is an indirect jump offset 50, it will actually update the code as it's loading to say, and it's actually offset 50 plus this memory address, which changes everything, right? So there's a lot of reasons you can't hash memory. But you mentioned the word dynamic analysis, and what you showed was actually a static call trace. So when I hear dynamic analysis, it's running in a sandbox, or are you actually extracting the call graph?
So dynamic analysis, from my perspective, it's keeping state space, right? So one of the things that keeps state space of is the call. So the call, like the stack when you do a call, right? So I'm preserving that stack. So it's not fully full emulation, it's pseudo emulation, but it is dynamic in the sense that you're preserving state. And so, and one of the reasons why I want to do this is that one of the challenges I mentioned, if you're doing it in the sandbox, there may be paths that may be difficult to get down because there may be constraints that won't allow you to, like in terms of normal code. And so, with this approach, you can force, you can go down whatever code path you want in an automated fashion. So that's really but that's a very good point, though.
Great talk, loved it. As long as you're interacting with the memory on these endpoints, have you considered the possibility of maybe a second round of this, going and asking via recall or volatility, run commands like psxview or something, and basically look for hidden process, look for other aspects or characteristics of that, and then incorporate that into subsequent rounds of analysis?
Yeah, that's a great question. That's really one of the next steps when you start looking at sophisticated malware, because I showed you a picture before where you you had this image, and then there's some free space where the malware writes its code. And so there is very, like, Poison Ivy was a classic example where the malware was like there'd be a code chunk of memory, and there'd be some gap, and then some more space, and so it made it hard for the assembler to detect that. And so those are tricky things, and I think that's really the next area of research is how do you detect those types of things so it can feed into this. So that's a really great point. Thanks for asking that.
Hi. So this question is going to be very, I think, basic. Someone with less of a cybersecurity background, although you said you studied game theory, so I'm, first of all, very impressed with how in the weeds you are on all this stuff that is over my head. So my very basic question to confirm my understanding is when you're looking at the n-grams and the static analysis, is it literally an n-gram of the 0, 1s in the binary representation?
No, so here's an example here. So this is really the Hello World x86 example here. So you have these instructions that'll produce hello world. And so one of the things that I look at is I look at the mnemonic. So the move instruction, that's the mnemonic I look at. So I ignore the stuff, I just look at the mnemonic here. So basically I do a sliding window. So these are the n-grams right here that I use. And so I can map those to the vector.
Okay, thank you. And so you do that in the phase 1 analysis, and then it's the same similarity measure you're using in the phase 2.
Or a different one. So very related. And so back to the question in terms of dynamic analysis. So one of the things I like to do is incorporate more dynamic analysis. So one of the challenges with malware with just pure static analysis is that a lot of times the calls can be obfuscated. You know, they can do relative address calls. And so with this VexIR emulation approach, you can keep track of the address and the call addresses, the relative addresses, so you can figure out what the call is resolved to. And so that's another feature that I like to add to extend this pseudo dynamic analysis model to make it closer to full-blown emulation. Any other questions?
You want to shout it?
Yeah, so I've been focused more on machine code, and he's asking about interpreted code. So can these techniques be leveraged for interpreted code? And so I'd say yes. I think that's really one of the next steps, because really a lot of malware right now, that's what happens. They're using more of the .NET, the Python scripts, and Bash, and like other things to kind of execute that code. And so that's another interesting path that I'd like to explore leveraging these techniques for, and that'd be very relevant and very important.
Malachi, I thoroughly enjoyed that.